The mean value theorem. The mean value theorem says that if f is continuous on a closed interval and differentiable in that interval AB, then there's at least one point in the interval so that the derivative at that point is that average slope, that average rate of change from the endpoints. So if you look at it graphically, we have a point x equal a and x equal b. Now, in this one, we're not guaranteed the ends have the same y value. They can have different y values. But if you took that average rate of change from these 2 points, from a f of a to b f of b, that average rate of change is just the slope of that line. So the slope of that line is the f of b minus f of a over b minus a. Okay, so what this theorem says is that take that slope, that average rate of change, from the beginning and the end point. You're guaranteed to have some point in that interval, some point C in between A and B, that has that same slope at that point. Okay, so whatever that average rate of change is from the beginning to the end, there will be some point that has that same derivative at that point. So that's what mean value theorem guarantees us of, and you do have to have a continuous and differentiable function. Okay, so now I'm going to go through a little sketch of this proof. To prove this, you actually use the Rolle's theorem. So what we're going to do is we're going to look at these points. We have A f of A right here, and we have B f of B right here. You know what the slope is between those, the line going through those 2 points. So the slope of that line, I'm going to call this line here L. The slope of that line, slope of L, will be f of B minus f of A over B minus A. Okay? Okay, now to prove this, what we're going to do is we're going to define a new function. This new function is going to be called g. We're going to have g of x. And this function g is going to be looking at the distance between the original function f here and the line going through the 2 points, a f of a and b f of b. Okay, so that means at the end points, if we're looking at the distance between the function f and this line L, the distance between them will be 0 at the end points. Okay, so this function g of x that I'm using is going to be f of x minus the L of x. Okay, so now what happens then is that g of a, which will be f of a minus L of a, well, f of a is L of a. Okay, and g of b will be f of b minus L of b, and that also is going to be 0. Okay, so what I've got is I've got the conditions for Rolle's theorem. By Rolle's theorem says that if I have a function that's continuous and differentiable and the endpoints of the interval, so I've got the interval from A to B, since g of A is equal to g of B, they have the same y value on the interval from A to B, then I'm guaranteed then that there is a point, so there is a number C in the interval AB, so that f prime or g prime of C is going to equal to 0. So that's just a result of Rolle's theorem. Well, g prime though, g prime of x, just going back up to the original function, is f prime of x minus L prime of x. Okay? Now, what is L prime of x? Remember this line over here, L of x, it's a line. So the slope of it is the derivative. So L prime of x will be that slope. So f of b minus f of a over b minus a for all x in that interval. Okay, a line has a constant slope. Okay, so now looking back at this equation, I have the G prime is F prime minus L prime. Specifically, G prime of C will be F prime of C minus L prime of C. But G prime of C, we know, is 0. That's the result from Rolle's theorem. So if this is 0, that means then that F prime of C is equal to L prime of C. Okay, but L prime of C, for any number in that interval AB, we know that that's F of B minus F of A over B minus A. So we've just showed that there is a C in between A and B, so that the derivative at that C will be that slope of that line going through A F of A, B F of B. Okay, so now I want to look at an example where we find the value in that interval. So we've got a function f of x equal 2x cubed minus 3x plus 1, and I want to show that it satisfies the conditions of the mean value theorem. Well, it's polynomial, so it's continuous, it's differentiable. The endpoints do not have to be the same. So what I want to do is I'm looking at the interval from minus 2 to 2. So my a is negative 2 and my b is going to be 2. I want to see what the slope of that secant line going through those two endpoints will be. So I have f of negative 2 will be 2 times negative 2 cubed minus 3 times negative 2 plus 1. So I've got 2 times negative 8, so negative 16 plus 6 plus 1. So I'm going to have negative 9. And then f of 2, 2 times 2 cubed minus 3 times 2 plus 1. So I've got 16 minus 6 plus 1 will be 11. So now the slope, f of b minus f of a over b minus a, the slope of the line segment passing through those 2 points. So the slope of this line going through these 2 points is what I need to find. That is 11 minus a negative 9 over 2 minus a negative 2. So I've got 20 over 4, which is this 5. Okay? So the slope of the line connecting those 2 endpoints is 5. So what I want to find now is what point in between negative 2 and 2 has a slope of 5, a derivative of 5. So find the derivative, f prime of x will be equal to 6x squared minus 3. I want to know when that derivative is going to be 5. So the x that makes that 5, I'll have 6x squared equal to 8. That means that x squared will be equal to 4/3. That means that x then is equal to either plus or minus the square root of 4/3, which will be just 2 over the square root of 3, or 2 times the square root of 3 over 3 if you want to rationalize it. So that gives me 2 numbers, 2 to the square root of 4/3 and negative the square root of 4/3. Okay, and both of those are in between negative 2 and 2. And if you look at the graph here, we have, this is negative 1.15 is approximately the square root, negative square root of 4/3. The slope of the tangent line there is the same as it is here, and that's the same as the slope of this tangent line passing through the beginning and ending points.